Hey everyone. In this video I'm going to talk about linear, logarithmic, and other transformations in the context of linear regression. And as we've seen in a lot of the applied examples that we went through both in previous lecture videos as well as in our Q&A session, it's not always best to fit a regression using data in their raw form. And there are two different types of reasons for that. On the one hand, we've seen, particularly with interactions, that there are problems with direct coefficient interpretation if we use predictors in their raw form. So there's a problem with interpretation in some cases, at least when it comes to the raw coefficients. But there can also be problems of model fit, right? Depending on the type of outcome variable, if it's a strictly positive outcome measure, for example, or a strongly skewed outcome measure and things like that, we may be able to improve our model fit and improve our predictions, essentially, ultimately, using other types of transformations, okay? So in general, whenever we talk about linear transformations in the context of linear regression, these linear transformations don't affect the model fit. They are usually just used to improve interpretation of particular coefficients. And whenever we talk about nonlinear transformations like the logarithmic transformation for outcome measures, for example, that ultimately kind of changes the underlying data generating process that we're modeling, and therefore also affects the interpretation, but also affects the fit. Okay. So to kind of outline that in a little bit more detail, I'm going to go through some examples step by step. So the first thing we want to kind of review again, and we talked about this in past videos and even in the last semester for a little bit, is linear transformations, particularly in the context of interactions. Okay. So as we know, the slope coefficient here, beta 1 and beta 2, even if we didn't have an interaction, the slope coefficient kind of represents the average difference in our outcome measure y, comparing items that differ by 1 unit on that particular predictor and are otherwise identical. Okay, and so obviously this is a little bit more complicated, including an interaction, because here now the kind of average difference in y is conditional on the second predictor, right? So for now assuming that beta 2 here in this case is a dichotomous indicator, and these red dots are cases where x2 is equal to 0. We have beta 1 as the expected average difference in y for 1 unit increase in x1. So this is this beta 1 here, and taking into account the interaction term for observations where x2 is equal to 1, the slope changes due to the interaction effect, and the average difference in y comparing items that differ by 1 unit on x1 where x2 is equal to 1 is actually beta 1 plus beta 3, right? Because we have to add this interaction term, okay? In addition, we can of course interpret the intercept as the expected value of the dependent variable for x1 being equal to 0 and x2 being equal to 0. That's the beta 0 here. And then we can interpret beta 2 as the expected difference in the outcome comparing two groups of observations, both of which have x1 equal to 0, but x2 takes the value of 1 rather than the value of 0. So that's the difference between those two lines at the point of x1 being equal to 0. Okay, so that's the quick summary of interpreting a simple interaction with one continuous predictor and one dichotomous predictor. Okay, so why can things go wrong in this case? In general, things can go wrong for two different reasons, or interpretation can be kind of not so simple for two different reasons, right? So in Ultimately, what this comes down to is one, the question of scaling. So to what extent, since these coefficients always represent the expected change that is associated with a 1 unit change in x, this always kind of, when we want to interpret these coefficients, and to what extent this interpretation is useful for us, always depends on whether this 1 unit change in x, or this difference in 1 unit is actually meaningful, right? And so one example that is pretty straightforward is, for example, if we're looking at GDP per capita, or something, a measure that takes very large values, and we're actually measuring GDP per capita in dollars as a predictor, right? $1 increase in GDP per capita is probably not the most useful unit of measurement if we're actually thinking about, okay, what is the substantive effect that, or the substantive difference that we're observing, right? So in those cases, we might want to change the scaling, the unit of measurement, to say, okay, a 1 unit increase should be 1,000 or $10,000 in GDP per capita, or something like that, right? So in order to have a proper scaling of the predictor, right? The same holds for our outcome measure, right? So we could think of similarly scaled outcome measures that take on very large values, where we might want to look at changes in thousands of dollars or something like that. Okay, so that's one issue: scaling. How meaningful is a 1 unit change actually, and to what extent does it help us to actually evaluate the substantive effect size. The other aspect that I mentioned a couple of times is implicit extrapolation for x equals 0, right? And this is kind of driven by the fact that both, especially with interactions, but also even without interactions, the intercept is interpreted as the average, or the expected average in the outcome for x being equal to 0. And this coefficient here for our dichotomous variable that is part of this interaction term is again the difference in the expected average outcome for x1 being equal to 0, right? So the question, of course, is whether x being equal to 0 or x1 being equal to 0 is actually kind of within the range of reasonable values that you would expect, or whether that is kind of an extrapolation far outside the range of values that are actually reasonable, right? We had examples where you looked at IQ scores as a predictor, right? And so you obviously, no IQ measure ever takes the value of 0. So it ranges between 70 and 130 or something like that, right? So any intercept, or kind of this main effect, if we have an interaction, would kind of lose any any reasonable substantive interpretation, because it's an implicit extrapolation outside of the range of data that we actually observe. Okay, so that's the second issue where we have problems with interpretation using the raw scales. Okay, and so in both of these cases, we can rescale and center the predictors and or the outcome measures to facilitate coefficient interpretation. Okay, and they're depending on your substantive problem, depending on what exactly your outcome measure is. There are different types of strategies and different kind of ways this can ultimately you can actually kind of transform and rescale these measures. Okay, some examples that are mentioned in the textbook are obviously just what I mentioned: changes of units of measurement for predictors and outcomes. I mentioned this example of GDP per capita in dollars versus GDP per capita in thousands of dollars. We're going to look at a measure in a second where we look at height. Height is measured, a person's height in our case will be measured in inches. You could think of, what if the data was collected where the people's height was measured in miles. Obviously that doesn't make any sense, because the range of values would be very small. But in cases like that, you would want to change the units of measurements for either the predictors or the outcome to bring it on a more interpretable scale. We talked about centering predictors for models with interactions. Mostly the key point here is x1 or the case where x is equal to 0 to be within the range of observable data. The easiest way to kind of achieve that is to just subtract the mean from all the average, the sample average from all observations. That way x being equal to 0 is equal to the sample average, and that's directly interpretable. And so that's a common strategy as soon as you have interactions and you're interested in interpreting the coefficients directly. We also talked about standardizing using z-scores, so subtracting the sample average and then dividing by the standard deviation to compute z-scores for the predictors. In the textbook, what Gell-Mann actually recommends is not dividing by one standard deviation, but by dividing by 2 standard deviations. And the reason behind dividing by 2 standard deviations is that ultimately, whenever we're standardizing predictors, we're interested in comparing effect sizes relative to the distribution of the distribution of the underlying predictor. Okay, and we can compare the effect sizes between 2 different predictors by looking at what one standard deviation increase, what kind of an effect one standard deviation increase has. Right, if we divide by 2 standard deviations, then we're looking at the kind of change in the average predicted outcome for a 2 standard deviation change. Okay, and the advantage of looking at a 2 standard deviation change, so going from -1 standard deviation to +1 standard deviation, for example, is that this is roughly equivalent to the comparison between to compare it to dichotomous indicators, right? So if you use this standardization with a roughly with a dichotomous indicator with around or roughly equal proportions, so basically the proportion of zeros and the proportions of ones is around 0.5 each, then the standardization will result in this dichotomous indicator ranging from around minus 0.5 to plus 0.5. Okay, so basically by using the standardization and dividing by 2 standard deviations rather than 1, we make dichotomous indicators and continuous predictors more comparable, if that is our goal. Okay, so that's just one kind of little trick to keep in mind. There are, of course, disadvantages with standardizing based on sample deviations. The key here is that those are sample standard deviations. The key here is those are sample estimates, right? So whenever we have not a representative sample or a very small sample, small number of observations, then the standardized predictor is kind of inherently related to whatever standard deviation you observe in that particular sample, right? And if your sample is small, if you're, then collect more data or try to compare this to a different data source with a different standard deviation, then you can't really make these comparisons the same way, or you can't make cross-sample comparisons as easily anymore, because the standard deviation between one sample and another sample might deviate quite a bit, particularly if your sample might not be representative, for example. Okay. So whenever that is the case, what you can do is you can, rather than using sample standard deviation, you can standardize using for example, externally specified population distributions, right? So if you know, for example, you have a sample of IQ, a sample of people who scored a certain score on their IQ test, and from the learning or from the learning psychology literature what the standard deviation of the IQ score usually is, you can use the kind of externally specified population distribution to standardize your sample, for example. You could also use conventional centering points, right? So rather than using the average, the sample average, you know, I mentioned IQ scores as an example, you could use you know, for the IQ, you know, use a score of 100, even though that's not your sample average. You could use that as the the centering point, because that is kind of, you know, that is meaningful from a substantive point of view. Okay. So there are different strategies. Of course, which one is the correct one depends on your specific application and what exactly your goal is and how you want to interpret your coefficients in your particular application. Okay. The key point here to understand, and that I want to emphasize again, is, oops, I'll move myself up here, is that these linear transformations are only about interpretation, to facilitate interpreting these coefficients, right? They're directly interpreting these coefficients, right? Linear transformations of either the predictors and or the outcome measure do not affect the model fit or the underlying predictions, right? The underlying model that you're fitting is still the same. All you're doing is basically, you know, changing the scaling of these axes, right? The underlying relationship between these measures is still the same. The underlying coefficients are still the same. And in fact, in one optional problem, or in the last question in your problem set for this week, or that is due at the end of this week, you'll have to show how linear transformations kind of still lead to the same differently scaled coefficients, but ultimately lead to the same predictions. That's going to be an optional question, or if you've already seen it, you'll see that you've seen that it's an optional question. But I encourage you to check that out, and you'll get some extra credit if you can kind of show that analytically as well. All right, so after kind of providing this overview, let's go through a quick example. But we're already at 15 minutes, so I'm going to take a break here and then show this in the next video.